Hey you guys, welcome back. So today we're going to be going over Level D, Lesson 2. This is about exponents and square roots. And we're also going to be talking about the concept of scientific notation and the order of operations. So let's go ahead and without further ado, we will jump right in and get started. So the first topic we're going to cover here is going to be about the order of operations. So what this is you may have heard this terminology before, PEMDAS. And so if you have a pretty good understanding already of what order of operations is and how do you apply it, you can skip and breeze right by this section. If you don't, that's cool. We're going to go over it right now. So the order of operations is what tells us the correct order to do things in an arithmetic or a mathematical problem. So it's really easy when you have something that's pretty basic, like 3 times 4, because there's only one operation here, and the operation is multiplication. So you're just multiplying 3 times 4, and there's nothing else for you to consider or look at. But most of the time, we have more difficult or complex problems that have multiple operations within them. And in order to keep the math problems that we write and that we do kind of more simple to see and read, we just put all the operations all together in one long statement, and then we have to remember in our heads what's the right order to do the operations in order to solve that. So the order of operations looks like this. This is actually a really good acronym that you can use to remember it. It's called PEMDAS. So I want you to until you absolutely have this completely memorized and down, like every time that you're doing any kind of math from now on, I want you to just make sure that you jot down PEMDAS. Oh, you can't see that. Let me scroll up. I want you to write down PEMDAS at the top of your paper. And the reason I want you to do that is because I want you to get in the habit of remembering this is the order I have to do these things in. Okay? So, the first thing in PEMDAS is parentheses, and really that would be like any kind of grouping symbol. So it could also be like you might see like brackets like this, or you could see braces that look like this. Okay, I'm really not that great at drawing them, but those are also grouping symbols, and so those fall under the category of P or parentheses in PEMDAS. So you always do grouping symbols first. And so wherever you see things inside grouping symbols, you go to those things first and simplify the inside of those grouping symbols before you start doing anything else. And I'll show you how we apply that in these examples. The next thing is exponents. That's what the E stands for right here, exponents. So you can see in this problem that they have a to the power of 2 or a to the second power. We're actually going to talk about exponents in this lesson today. So if that's confusing to you, don't worry. We'll get to that in a little bit. The next section is M and D. They're grouped together and they're the same color here, and that is on purpose. That's for a reason. Because you do all multiplication and divisions from left to right in the problem, okay? So this is from left to right. And the same thing is going to be true for addition and subtraction. You're going to go left to right, okay? Because you could have multiples. You could have pluses and minuses. You could have multiply and divide. And you just want to, you can do them at the same time. You don't have to do one before the other, but you want to go from left to right, and that's the correct order of operations. The last thing is addition and subtraction. That's plus and minus, and that is PEMDAS. So let's go ahead and apply this so we can do some of these examples. So here we have 3 times 9 plus 7. So according to the order of operations, let's think about what our operations are. So first we have a multiplication and then we have an addition. So this is actually already in the right order. We're just going to go left to right because multiplication comes before you do addition. So you're going to do 3 times 9 first. So you have to figure out 3 times 9. And then the second step will be for you to add 7 to that answer, okay? So if we were to simplify this, 3 times 9 is 27, but we still have that plus 7 on the end. Now we only have one operation left, which is addition, so we're going to add 27 and 7, which is 34. Okay, next problem, next example. We have 9 divided by 3 plus 4 times 6. So the order of operations says that you do multiplication and division before you do addition. So that means we're going to be doing this operation and this operation simultaneously from left to right. And then whatever those answers end up being, we're going to be adding them together. So let's use my red pen. That's our second operation there, okay? So 9 divided by 3 is 3, and you still have that plus sign in the middle. And then you have 6 times 4, which is 24. And when you add them together, you get 27. Okay, the last example here actually works in some parentheses to this problem. So there's 2 sets of parentheses here. And basically you can look at this like whatever happens inside here and whatever happens inside here, you're going to figure those out first, and then you're going to go ahead and divide them. Okay, that's your second step. So let's figure out the first parentheses, right? So what you can think of this as is you can sort of think of this as like 7 times 8 minus 4. We're going to do that first. So let's figure out what this simplifies to. And the way you can figure this out is by looking at the order of operations inside this parentheses. You have a multiplication and a subtraction, and so multiplication comes first, which means we're going to do 7 times 8. And then the second thing we're going to do is we're going to subtract 4. So if we do 8 times 7, that is 56. And then we're going to subtract 4, which is 52. So this whole thing here is now 52, and there's still a division here. And then we need to do this other parentheses, which is 6 minus 2. And there's only one operation to focus on here, so you just do that subtraction and you get 4. And now we have 52 divided by 4, and I'm not even sure that that comes out to something. Oh, it does, 13. Okay, great. So the final answer is 13. And that's by doing 52 divided by 4 equals 13. If you do the order of operations out of order, like you do one operation in the wrong order, do the wrong step first, you will get an answer that is not correct, okay? You may have seen, if you guys are on like social media and stuff, you may have seen like all of those memes and stuff that go around with like the 8 plus 2 divided by 2 minus 2 or something like that. I forget how it goes. If I find it, I'll post it on Google Classroom later. But if you've seen that, you see how they arrive at 2 different answers. And the reason that's happening is because they're not doing the order of operations correctly. It's meant to trick you, okay? So that's it for order of operations. Just make sure that you have PEMDAS, something that is ingrained in your memory, and that you know how to apply it, because it's important for every type of math problem that you do, because whatever you're solving, you need to make sure you go in a particular order. It's kind of just like cooking, right? So like if you're making a cake, you might like mix your dry ingredients first and then mix your wet ingredients like separately. And then you might combine those together and pour it in the cake tin. And so there's like a very specific order or a procedure that you have to follow to get to the correct answer. If you just started mixing everything all at once, the batter might be too thick or have air bubbles or something like that, and then your final product won't be a cake, it'll be, something else. I've never actually cooked a cake wrong, so I don't know what it would turn into, but you get the idea. So the next thing we're going to cover is exponents. And so go ahead and pause the video, make sure your notes are on par here, and then when we come back, we're going to start with exponents. All right, so let's continue. We're going to talk about exponents. And if you've heard this terminology before, great. If you haven't, we're going to cover what it means right now. An exponent is just a fancy word. It's a shortcut that we use in multiplication in math, and it means repeated multiplication. So it's kind of like a notation above the number. So see how you have 2 to the power of 4 right here? That's something that you would say. So make sure you jot that down, okay? 2 the power of, or you might use like the plural of this term, of this word up here for the number. So you might say like 2 to the 4th power, okay? 2 the blank power. Or if it's like a 2, you might say the 2nd power, or the 3rd power, 3 and then rd, 3rd power. Those are some ways that we say things about exponents. So it's a notation that we write in superscript. It's tiny print that's smaller and above the number. So see how this is kind of like above the line here? All of these numbers are on your standard line that you write on, but the superscript is above and it's a little smaller. It's meant to like show a notation or denote something about it. That's what superscript is used for. And the same thing for subscript. That's not written here at all, but a subscript would be something that's like down here. And yes, we do use that in math. I don't know if we're going to cover that, any applications of that in this course, but that's just a little tidbit from me to you. So exponents, when you have an exponent, you have a base and then an exponent or an index. It's called both things. As we move forward into higher math, we prefer to use the word index because you'll also use that with roots and stuff. So we're not there yet, but that's something you might want to keep in mind. This could be an exponent or an index. It's used, both terms are used for it. And what does it mean? So what happens when you have an exponent or an index above a number? So what it means is that you do repeated multiplication. So whatever this base is right here, you're going to multiply by itself this many times. That's it. That's all an exponent tells you to do. So really, 2 to the 4th power just means 2 multiplied by itself 4 times. So 2 times 2 times 2 times 2. And the answer to that would be 16. So 2 to the 4th is 16. If you've probably seen this before, it might be like 2 squared equals 4, okay? Or 3 squared equals 9, okay? And I thought I had put some... Oh, I did. They're at the bottom. Okay. Okay, so we're going to do some examples of how you apply exponents now. This is actually the top of the next page. But at the first example, you have 5 to the 4th power, or 5 to the power of 4, which all this means, I have big handwriting, so I'm going to draw it over here. This is question 1. All it means is 5 to the 4th is 5 times 5 times 5 times 5. And so you can break this down. You can use a calculator if you want to. There's a way to input exponents on a calculator. I actually don't have a basic scientific calculator here. I only have a graphing one, so I'm not going to be able to show you that. But I'll find a video and I'll post it for you guys. That way you can see on common calculators how to plug this stuff in. If I forget to post that, somebody please message me and remind me to post that for you, because whatever calculator you have at home, I want you to be able to use it properly. You could also break this down by just breaking it down by parts. Like, 5 times 5 is 25. And then that's multiplied by 5 times 5, which is also 25. And 25 times 25 is 625. So that's one way you can do it. You could just go piece by piece. So 5 times 5 is 25. So 25 times 5 times 5. And then you can do 25 5 times, and that would be 125 times 5. And then you can finally do 125 times 5, which is going to give you 625. A couple ways to do that. You just keep increasing that by a factor of 5, or honestly, the shortcut, the thing that most people do at this point these days is just plug it in the calculator. It's the important thing is that right now today, how do you break this down and actually calculate it? But in the future, it'll be acceptable to just use the calculator. Okay, so I'm going to switch colors to do number 2. That way we don't blend them together. This is question 2 here. We have 4 to the third power plus 3 to the second power. So 4 to the third plus 3 to the second. So you need to break down both of those exponents, okay, and do them separately and then add whatever the answer is together. And the order of operations sort of tells you to do it that way, because if you remember PEMDAS, okay, oops, let me roll that over. If you remember PEMDAS, right, here's PEMDAS. The exponents come before addition. So you have exponent, and you have addition, and that's all the 3 parts of this problem. So the exponents come first, and then the addition comes at the end. So we need to do 4 times 4 times 4, that's 4 to the third, and add this to 3 times 3, okay? So we can break this down. 4 times 4 is 16, and 16 times 4 is 64, plus 3 times 3 is 9. So if we put this together, that's 673 that's left there. 673 would be your answer. Okay. Now I think there's part of the delta math goes over order of operations, and exponents is actually part of that, so you'll get practice with that when you go do the order of operations part of the assignment, okay? So the next part of this section is about scientific notation. Now this can get a little tricky, so make sure that you have basically like eliminated all the distractions from your surroundings, and let's really tune in and focus here, because you can get lost easily on this, okay? Scientific notation is just a shortcut, okay? It's a shortcut that we use in math and also in science, mostly in science, to express numbers that are like really, really large that have a ton of zeros, or really, really small that have a ton of decimals, okay? And I gave this example in the description up here, so let's read through it together. Imagine if we wanted to count the entire population of the Earth, the planet Earth. There's approximately 7.594 billion people, which if you write that number out, like with all the zeros and everything, it comes out to this. It's a huge number. Now, we can use scientific notation to shorten this number, which will make it easier to read. If you remember, back in the last lesson, we talked about percents, and we talked about how you can move the decimal point. Well, in scientific notation, that's a major component of that is moving the decimal point. Okay. The only thing, so your final answer is going to look like this, right? It's going to have some number. It has to be between 1 and 10. So this number here is going to be less than 10, and I'll show you how we get a number less than 10. And then it's going to be multiplied by 10 to some power, okay? Now the power here, this right here is how many times you move the decimal. Okay, and I'm going to show you exactly how to do that right now. So let's look at this first example. We're going to express this number, the billions of people right here, in scientific notation. So we know, I'm going to zoom in a little, we know that the decimal point of this number is here, because it's a whole number, right? And what we want to do is we want the decimal point to be here, because if it's there, then we'll have the number 7.594 or whatever, and that will satisfy this requirement, meaning this C value has to be less than 10. So count how many times you have to move the decimal to do this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 7.594, drop all the zeros, times 10 to the ninth. Easy as pie. All we did was use the number of times we moved the decimal as our exponent here on this 10, okay? And whatever is left over, the number here that's less than 10, that, and not including all these zeros, is what you would write times 10 to the ninth power. And these things are equivalent. These are equivalent numbers. This is a shortcut for us in science so that we can look at this and generally say, oh, it's 10 to the ninth power, so this is like a really big number, okay? We can do the exact same thing the other direction, okay? And all that's different is that you have a negative exponent, okay? So if the decimal moves this way, okay, to the left, right, then you're going to have a positive exponent. And I'm talking about this number right here, the red number. If the decimal has to move to the right, then you're going to have a negative exponent. Okay? So let's apply the same thing again, and let's do it with this quantity. It's a really, really, really super small amount of milligrams of something. It doesn't say what it is. It could be like a medicine or a poison or like some quantity of something. And this is really, really super small because look at how many zeros there are in front of this, right? This is not 0.94 milligrams, which is almost one whole milligram of something. This is 0.00000000094 milligrams, and it's super small. But we're going to express this in scientific notation. So we have our decimal point, here it is, and we want it to be right here. We want it to be 9.4. And the reason we want that is because then we'll have a number for our C value that is going to be less than 10. So how many spaces do we move the decimal to the right? You're going to take it and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is going to be 9.4. That's where we move the decimal to, times 10 to the negative 11, okay? The reason it's negative is because what happens here is you're taking this 9.4, which is a quantity that you and I can relate to pretty easily, right? We can recognize 9 as like an easy to look at number. And this means move the decimal to the right. This means move the decimal to the left 11 spaces. And so if you were to do that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, you would end up with this super small quantity with all of these zeros in here. Now you might be wondering, what's the background here? Why do we do this, okay? And there's a whole concept or principle in science and in scientific experiments which has to do with significant digits. So typically a 0 is not a significant digit, and so it is a waste of space, a waste of time, a waste of brain processing power to write a number out. Let's say you're writing like a scientific report and you did a population of ants in all the ant colonies in South Florida. So that's going to be a huge number, right? Like trillions of ants probably, okay? If you were writing a paper, right, and you're writing there are X amount of ants, and in this area there's this many ants, and there's this many ants, all those times that you write those numbers, if you were to write them out with all these zeros every time, your paper would be super long and very difficult for the brain to process. So we use scientific notation to show that whatever this quantity is that we measured is super large or super small based on this exponent right here, okay? And it leaves off those insignificant zeros. And that's really the background of it. That's why we have scientific notation. It, may or may not be exactly applicable to the field that you personally are working in or planning on going into. But still a mathematical skill that is good to know so that you can apply this later. It'll definitely be on your GED test. So, don't breeze by this, okay? There's something else you can do with numbers that are in scientific notation, and that is multiplying them. So we're going to talk about that skill right now of multiplying the numbers that are in scientific notation. I think I need to make this a little smaller so we can see everything. So there's a very specific order to do everything in. Okay, and we're going to show you how that works right now. Here we have two numbers in scientific notation, right? Okay, so look at what I'm pointing at right here, okay? You have some number that is less than 10, okay, times 10 to the whatever exponent, and then 5 times 10 to the whatever exponent to the fourth power. And these would both, you'd say, are in scientific notation, because remember, in scientific notation you have c times 10 to the power of n. That's your basic form for scientific notation. So these match that, okay? Both of these individually match that. But these are being multiplied, okay? The reason I know that is because when you have parentheses like this, I don't know if we've covered this before or not, but when we have parentheses like this that are butted up against each other here with no operation inside, the assumption here, right where my pen is pointing, the assumption here is that you're multiplying, okay? So don't forget that. This is multiplication, okay? All right, so how do you multiply these? Well, basically the procedure you're going to follow is you're going to multiply the numbers, the first numbers, which is called the coefficients, okay? So 3 and 5. And then you're going to add the exponents. And that is all there is to it. The only thing you might run into is when you get to your final answer, do you see how 3 times 5 comes out to 15? But our value for c here, this first number, it can't be larger than 10. So we have to move the decimal point, and I'm going to show you what happens. So 15 times 10 to the 6, right? This doesn't work. The decimal point is right here. We actually need to move the decimal point this way, 1. And so what happens when you move the decimal point to the left, 1? If you go to the left, you are increasing the exponent. So this is the same thing as 1.5 times 10 to the 7th power. You're increasing this exponent, okay? That's how it works. That's multiplying numbers in scientific notation. The first step is going to be for you to multiply the coefficients. Multiply this and this. And the second step is going to be to sum or add the exponents. 2 plus 4 gives you 6. Okay, I'm just multiplying, I'm highlighting here so you can see the result of everything. All right. I don't have any scientific notation problems where you're multiplying inside the notes. However, in the Delta Math assignment, there are practice ones for this. So if you follow this procedure every time, you will be in good shape. Just remember your final answer, okay, this value has to be between 1 and 10. Okay, it has to be between 1 and 10. So you may have to move a decimal point, and get that in the right place, all right? Cool. So if I'm not mistaken, I think square roots is the last piece, and then simplifying. Okay, so square roots is the last component of the notes of this topic. So go ahead and hit the pause button, take a bathroom break, get refreshed, and then when you come back, we're going to be working here on square roots. All right, so the concept of a square root or squaring a number actually has a basis in geometry. So if you remember, a square is an object in geometry, a two-dimensional object that has the same length on its sides all the way around. So if you look at this example right here, this is a square where the length is 3 on the side and also on the top. That would also mean this one and this one are 3. And if you were to break down the square into equal units, 1, 2, 3 makes up the length here, and 1, 2, 3 makes up the length here. So there must be 9 of these little squares inside of this shape that are all of an equal size in order to make this up. And so that means that the area of this square would be 3 times 3, which would give me 9. And would you look at that? There are 9 units that are inside of this square. And that is where that term comes from. And actually, if you take 3 and bring it to the power of 2, that would be called squaring it. Okay, that's the exponent of 2, okay? If you bring 3 to the power of 2, that means you're multiplying 3 by itself like this, and 3 times 3 would give you 9. This is called a perfect square because when you square the sides and the sides are the same, the area of that square comes out to a perfectly even figure of a square. In other words, equal units on the inside that match or sort of mirror the math problem that we're doing. So that is basically the gist of squaring a number. That's where the terminology comes from. It really just means whatever whole number you're looking at, you're bringing it to the power of 2. Now, the opposite of squaring something is looking for its square root. So suppose that you had a square. Okay, we're going to pretend this is a square. It looks kind of like not so great, but whatever. I did my best drawing that I could. Suppose you're looking at this square here, and all you know is that the area is 9, okay? You might say, well, how can I find the side lengths? What is this? What are these two lengths here? What is it that you multiply together to get that? Okay, and 9 is a sort of like there's a pattern that we look at called something called a perfect square, which means that when you find the square root of this number, it's a perfectly even, clean, whole number, no decimals, nothing crazy going on there, just whole numbers. So a square root looks like this, okay? And what you would be doing is looking for the square root of 9. So in other words, what two numbers do you multiply together, okay, that give you 9, all right? Actually, wait, there's a better way for me to draw this. Let me just fix this real quick. Hold on. Okay, so the square root of 9, okay, is going to be a single number. And the question is, when you take that single number and you square it, or you multiply those two things together like this, you should get 9, okay? So what are the question marks here? What number goes in the blank for those question marks, all right? And you already know that 3 times 3 gives you 9. So 3 times 3 gives you 9, or 3 squared gives you 9. That means the square root is 3. The square root of 9 is 3. And the way that you sort of interpret or understand that is that when you find the square root of something, that is the number that you multiply by itself in order to get the number that you were originally looking at. Now, there's a whole set of perfect squares. If you start with the number 0, 0 squared would give you 0 times 0, which is 0. 1 squared, 2 squared, I'm going to scroll this down. 1 squared, 2 squared, 3 squared, 4 squared, and you can keep going, okay? And the results are numbers that have perfect squares. 1 squared is 1 times 1, which is 1. 2 squared, right here, 2 squared, is 2 times 2, which is 4. So the square, that's my highlighter. Sorry about that. Let me fix this so that I'm drawing with the correct thing. We'll use red, why not? That means the square root of 4 equals 2. And the square root of 9 is 3. And the square root of 16 is 4. And the square root of 25 is 5, and so on and so on and so on. And this is exactly how you must look at squares, taking the square root of a number, okay? I only listed the first 6 of them here, 1 through 6, but that's the gist. Now, when we're talking about, I'm going to highlight this. I bolded it, but we're going to highlight it too, okay? When we're talking about taking the square, come on, let me highlight here. Taking the square root of something, right? We're talking about a symbol called a radical. So the, let's see, is there an image for this? Okay, no, I didn't write one. Okay, so this right here, this symbol is called the radical. Okay, and then there's going to usually be some kind of number underneath that symbol. Okay, and the number, okay, so that's the symbol. And then this that's on the inside here, okay, the number on the inside is called the radicand. If you are a person who needs to write things down, maybe like on index cards or something, like flashcards to remember this vocab, I strongly encourage you to do that. You can do it on index cards, or you can go, we did an activity a few weeks ago with the geometry, and you had to go on Quizlet, and I made the flashcards for you. But you can go on Quizlet anytime you want, and you can make flashcards, and you can practice them on Quizlet. So I would highly recommend that you do that if vocab is not your thing and you need some repetition and some memorization there. The number inside the radical here is called the radicand. The symbol itself is called the radical, okay? A square root is the opposite operation of squaring a number. So when we do square roots in a problem, we do them as part of the E in PEMDAS. So I think, yeah, that's showing. We want to do that when we're doing the exponent part. So let's do an example. 3 times this quantity, 4 plus 4, minus the square root of 25. Lots of stuff happening here. PEMDAS says we do parentheses first, so we're going to do only this right now. So the next step would be 3 times 4 plus 4 is 8 minus the square root of 25. The next thing would be E for exponents. And when we get to that step of E for exponents, that also means we're doing the square roots. So the next step is going to be 3 times 8 minus, now what is the square root of 25? What number do you multiply by itself to get to 25? Now honestly, you're going to have to just commit to memory the list here, okay? And honestly, I would even go further than this. I would go all the way up to like 12 or 13. And just those numbers should be popping out at you like, oh wait, that's a perfect square. You know what I'm saying? So make a list, put it on Quizlet, and do that. The square root of 25 is 5, so we're going to correct that. And then the next thing that we need to do, we'll use orange for this, is multiplication. So the next step is going to be 8 times 3, which is 24, minus 5. And then the very last thing that we're going to do is just going to be the whole operation that's left, because there's only one thing left, which is subtraction. 24 minus 5 is 19. And that's your final answer there, okay? So that's the reason we went over this, is so you know how to work with it inside of operations. There's one more thing that you have to know how to do, a skill here called simplifying square roots. And so when you do that, you're going to be using a skill that we tapped into. We're going to be tapping into a skill we learned before, which is factor trees. Okay, you're going to be looking at the factors of the radicand, which is what's inside the radical, and looking to see if any of those factors are perfect squares. Because if they are perfect squares, you can simplify this problem. You can simplify the square root of 72. Okay, if you were to go to your calculator right now, okay, I'm going to pull up my calculator, and I'm going to plug in the square root of 72. When you do that, you're going to get some ridiculous number with a huge, like, non-terminating decimal. It's just going to go on and on forever. It's completely irrational. 8.485281374238857, blah, 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 blah. That's not useful to us. So 72 is obviously not a perfect square. However, there may be a perfect square that's a factor of 72. And so you want to start looking for factors of 72. If I take 72 and I break it down in half, I get 36 times 2, okay? 36 is a perfect square. It's in our chart from above, remember that? So what you can do here is you can rewrite this as 36 times 2 all under the radical. You are completely and totally empowered to do this because it's an equivalent statement. These things are equivalent to each other. They're exactly the same, okay? It's almost like you're working backwards, actually. Because if you had 36 times 2, you'd probably want to multiply that and end up with the square root of 72. Now, what do you do next? Well, there is a rule with square roots, right? If you have two things inside a square root that are being multiplied, this is the same thing as having the first one under a square root times the second one under a square root. Again, this is just a rule of math that you have to get used to and memorize. You can split your square root like this. This is totally legal and legit. Now, look at just this. What is the square root of 36? Well, you know what that is because it's a perfect square. It's 6. So you can change this to a 6 because that is true. The square root of 36 is 6. Everything I'm doing here is equivalent, okay? So your final result, your final answer is going to be 6 times the square root of 2. The square root of 2 doesn't break down any further, and so you're just kind of stuck with that the way that it is. But the 6 is a nice clean number that you could pull out of this square root, okay? Next example, we have a number already being multiplied here on the outside. That's okay too, okay? We're going to do one step at a time. Look at the inside of the square root. You have a 50, okay? Let's use purple for this. I'm going to draw a big line here. Let's use purple for this. So if I were to look at 50, right? I can break 50 down into 25 and 2. And already I know that I'm good to go because I know 25 is a perfect square. The square root of 25 is 5. It's in our chart here at the top. So if that's the case, that means I can rewrite this problem. So this will be step 1 here. You're going to have 3 times the square root of 25 times 2. Now remember what I said before, when you have two things being multiplied inside of a radical like this, you are completely empowered to break it apart into two different radicals. 3 times the square root of 25 times the square root of 2. Still an equivalent statement. We're good to go. It's still the same thing, okay? In math, remember, if you can find things that are equivalent, you can rewrite things and replace them with their equivalent statement, okay? That's totally okay. Okay, so the next thing is going to be, let me just slide this up a little. The next thing is going to be simplifying this because we know the square root of 25 is 5. So our next step is 3 times 5 times the square root of 2. Now, there's one more thing we have to do, which is this 3 times 5 right here, because you can completely simplify that. 3 times 5 makes 15. So our fourth step is going to be actually the answer, and it is 15 times the square root of 2. These are equivalent, okay? This is simplified. And that is the goal of simplifying, is looking for perfect squares that you can kind of pull out or separate and simplify them. All right, my friends, we have reached the end of this lesson today. The Delta Math assignment that I gave you guys actually yesterday included some stuff from this topic, so I'll go ahead and log back in there and wrap those up. After this lesson, you should be able to get all the way up to level D, lesson 2, and then when we come back next week, we'll be starting with lesson 3. If you guys need any help with anything on this, please feel free to reach out because I am definitely available to help walk you through any problems that you're working on, okay? Just send me a text or an email or comment on Google Classroom or something, and I will be there for you. All right, guys, until next time, I will see you later. Bye-bye.